You split a particle into two. You send one to the far edge of the galaxy, and the other stays here, right in front of you. They're separated by light years. Different locations, different fates, different futures, but somehow they're still connected. What happens to one instantly affects the other. No delay, no message sent, just cause and effect collapsing across the void. This is quantum entanglement, and it breaks reality in half. You see, in the world you think you understand, events are local. Push something here, and something here responds. But in the quantum world, distance doesn't mean anything. Two particles can be billions of kilometers apart, yet act as if they're still one. Einstein hated it. He called it spooky action at a distance because it violated everything he believed about the universe. In his world, nothing could travel faster than light. No influence could jump from here to there without crossing the space between. But entanglement doesn't care about distance. It doesn't travel. It just happens. The weird part? You can't see entanglement. You can't feel it. But it's there. Particles entangle and stay entangled, locked in perfect synchronicity until something breaks it. And when you measure one, you instantly know the state of the other, no matter where it is. And that's terrifying, because now you have to ask, if two particles can be entangled, can people? We're made of particles, our bodies, our thoughts, our minds. Are there hidden threads connecting us to others? Are we reacting to changes that are happening to someone else, somewhere else, without even knowing it? You start to wonder, have you ever felt something shift, like someone pulled a string inside you, and you didn't know why? What if that wasn't just emotion? What if it was entanglement? Some scientists have suggested the entire universe may have begun as a singularity, one unified state, meaning everything and everyone might still be entangled in some deep, fundamental way. Everything that exists now was once one thing, one particle, split apart into stars and atoms and people and thoughts. But the connection never left. And here's where it gets even darker. When you observe one half of an entangled pair, you collapse its wave function. You fix it into reality. But at that exact moment, you collapse the other two. Which means that what you choose to observe doesn't just affect what you see. It affects what's real somewhere else. A universe being sculpted by attention, by consciousness, by you. So maybe the scariest part isn't that the particles are connected. Maybe it's that you're responsible for something bigger than you could ever understand. That your gaze shapes reality. That your thoughts ripple into the void. Because quantum entanglement doesn't just suggest that reality is stranger than we thought. It proves it. There is no boundary, no true separation. Only a hidden fabric, silent, invisible, binding everything together. And the moment you try to unravel it, you realize something horrifying. It might not be the particles that are entangled. It might be you. You made a choice today. Maybe it was small, what to eat, when to speak, where to go, or maybe it was something bigger, something that changed the course of your life, and you told yourself it was final, that this was the reality you now live with. But what if that wasn't the full story? What if, at the very moment you made your choice, the universe split? Not metaphorically, literally, not symbolically, but physically. A fracture, a duplication, a split in the very fabric of existence, where two timelines now run parallel, one where you did and one where you didn't. This is the many worlds interpretation. It sounds like science fiction, but it's rooted in quantum mechanics, the most precise and experimentally verified theory in all of physics. And yet, within it lies the most mind-breaking idea we've ever faced: that the universe doesn't collapse into one version of events when something happens. It branches into all of them. When you look at the world around you, you see a single thread: a beginning, a middle, and a now. You believe events unfold in a straight line, that you are the sum of everything that's happened to you. But quantum mechanics says otherwise. In the microscopic world, particles don't behave like solid, fixed objects. They exist in states of superposition, a state where they're not just in one place or doing one thing, but in multiple possible configurations at once. And only when observed does that uncertainty collapse into something definite. But what if nothing collapses? What if instead the universe just forks, again and again, endlessly, each time a decision is made or a quantum event plays out? This is the heart of the many worlds interpretation, first introduced by Hugh Everett III in 1957. According to Everett, all outcomes of quantum measurements actually occur in separate, non-communicating branches of the universe. Every time a coin is flipped, one world exists where it lands heads and another where it lands tails. The act of observation doesn't eliminate possibilities, it multiplies them, and each version of reality becomes just as real as the one you currently inhabit. So imagine this: there's a version of you who didn't drop out, another who never met the person who changed your life, one who died in the accident you barely survived, and another who never even made it past childhood. They're all out there, still moving forward in their own versions of time, unaware of your existence, just as you are unaware of theirs. The you who kept writing, the you who gave up, the you who became everything you're afraid to become. All of them real, all of them you. But this isn't just a philosophical musing, it's a logical extension of quantum physics. When scientists perform the famous double slit experiment, they find that particles like electrons behave like waves when unobserved, interfering with themselves, as though they're in many places at once. But when observed, they suddenly decide on a single path, behaving like a particle. The classical interpretation is that observation collapses the wave function into one reality. But the many worlds view says it never collapses at all. Instead, you, the observer, split with the particle. In one universe, you saw it go left. In another, it went right. The particle didn't choose. Reality branched. And this isn't limited to particles. Because you are made of particles, so is your brain. So are your thoughts. Every process, every emotion, every decision is entangled with quantum events, which means that every you, every version of you, is playing out across infinite timelines. It sounds beautiful, in a way, that every missed opportunity might still exist somewhere, that the road not taken wasn't erased, just hidden. But it's also horrifying, because the same logic applies in the opposite direction. Somewhere you're the one who hurt them. Somewhere you said the unforgivable thing. Somewhere you're the one who didn't stop. There's a version of you who is the monster. And here's the twist: you'll never know. These parallel worlds don't interact. They're isolated, branching out like the roots of a massive invisible tree. You can't cross over. You can't visit. You can't reverse a branch once it's made. But you're not in control of it either. These aren't conscious choices spawning these worlds. They're automatic, relentless. Every quantum interaction, down to the smallest shift in energy, splits reality again. The universe is constantly fracturing into countless versions of itself with every passing moment. It means there's no such thing as a fixed future, no such thing as a single past. Only the present you happen to be experiencing out of an unfathomable web of possibilities. And that has implications, ones that stretch beyond physics, into psychology, into guilt, into hope, and into identity. Because if every choice is made somewhere, then what does it mean to be you? If your consciousness only rides one branch, are you really the one making decisions? Or are you just a passive observer, strapped to one particular version of the ride? What if free will is just the illusion of selecting one reality, while all others continue with or without you? And what about regret? How do you live with choices when you know that somewhere you didn't make them? Somewhere things worked out. Somewhere they didn't fall apart. Somewhere someone loved you back. Somewhere you never let go. It turns your entire sense of self into a ghost, a temporary passenger on one branch of a massive tree of possibilities. And you start to wonder, if every version of you exists, then what's the point of this one? What makes this version special? Why are you here and not there? Maybe the many worlds interpretation doesn't just challenge physics. Maybe it's a mirror, one that shows you just how fragile your reality is, how quickly it splits, how little it takes to become someone entirely different. Not tomorrow, not in theory, but right now, in this very moment. Because as you're hearing these words, your atoms are splitting paths. Your brain is fracturing into outcomes. Your world is branching, quietly, invisibly, inevitably. And somewhere out there, another version of you already stopped watching this. Another version never heard it at all. Another version kept going. So the real question is, which you are you? And how long will this version last? You think you understand time. You think you feel it pass. 1 second after another, one breath after the next. Steady, predictable, linear. But the truth is far more disturbing. Because time doesn't move the way you think it does. It bends, it stretches, it slows down. And it doesn't care how that makes you feel. This isn't just abstract theory. It's a proven part of the universe's design. A truth so strange, it breaks your sense of reality. Time is not absolute. It's relative. And it changes depending on how fast you're moving, or how close you are to a massive object. This is time dilation, a core prediction of Einstein's theory of relativity. And it has already been measured, tested, and confirmed. Again and again. Here's how it works. If you and I are standing still on Earth, time ticks the same for both of us. But if you were to get into a spaceship and fly away at near the speed of light, something strange would happen. From your perspective, everything feels normal. But from mine, something has shifted. To me, your clock is ticking slower. Your seconds stretch. Your minutes elongate. Time itself is lagging behind for you. And when you return, if you return, far more time will have passed for me than for you. Maybe a few years for you, but decades for me. This isn't fiction. This is what happens. It's not a theory. It's a consequence of how the universe really works. Time slows down the faster you move. And it's not just speed, it's gravity too. If you're closer to a massive object like a black hole, time ticks slower for you than it does for someone farther away. Get too close, and time could almost stop entirely. Remember that scene in Interstellar, where the crew lands on a planet near a black hole, and 1 hour there equals 7 years back on Earth. That wasn't artistic exaggeration. That was relativity. That was time dilation. And it changes how we think about everything. About travel, about aging, about death. But here's where it gets darker. If time is elastic, then so is everything that depends on it. Memory, regret, experience, identity. Who are you when time itself refuses to stay still? What does it mean to age when time doesn't pass the same way for everyone? What does it mean to miss someone when, from their perspective, they were only gone for a moment? Time dilation isn't just physics. It's emotional horror. It's isolation. It's losing someone, not to death, but to the warping of time itself. Imagine watching your child grow old while you float above Earth, barely aging, or saying goodbye to a lover, knowing you'll return looking the same, while they've been dead for decades. It's a paradox wrapped in loneliness. And here's the most haunting part. It's already happening. Right now. Satellites orbiting Earth experience time slightly faster than we do on the surface. That's how GPS works. If we didn't account for the difference in time dilation, your phone would be off by miles. Astronauts age slightly slower than we do when they spend extended time in orbit. It's subtle, but measurable, and it proves the point. Time is not fixed. It's not equal. It's not fair. And if one day we ever manage to travel at near light speeds, time dilation becomes more than just a curiosity. It becomes a curse. Because you could leave for what feels like a few years and return to a world that no longer remembers you. A world you don't recognize. A world that has moved on without you. So what is time, really? A measure? A rhythm? Or is it something much more fragile? Something that can betray you? Something that obeys no human logic? Something that doesn't care how many memories you try to stuff into it? Because when it stretches, so does everything you are. You become a blur, a shadow of yourself, detached from the very flow you were born into. Maybe time isn't a river. Maybe it's a sea. And you're drowning in it without ever realizing. So next time you say, "I don't have time," remember, that's only true here. Somewhere else, out there, near a black hole, at the edge of motion itself, you might have all the time in the world. You just won't recognize the person waiting for you when it's over. Black holes. We imagine them as cosmic vacuum cleaners. Silent, dark, merciless. A place where gravity becomes a god and light itself is shackled. But what if I told you they don't just devour matter? They swallow something deeper, something terrifying. Information, not data on a hard drive, not texts or files, but the very essence of what something is. A star, a planet, a person. Every particle, every quantum state, every arrangement of energy and spin, it all holds information. The universe runs on it, and yet black holes may destroy it. That's the paradox, and it threatens the foundation of physics itself. Here's the problem. According to quantum mechanics, information can't be destroyed. It's one of its most sacred laws. When something changes, burns, explodes, freezes, the information is preserved. Maybe scrambled, maybe hidden, but never gone. But then black holes enter the equation. According to general relativity, once something crosses a black hole's event horizon, it's gone. Nothing escapes. Not even light. And when the black hole evaporates, yes, evaporates, through a process called Hawking radiation, it eventually disappears, leaving nothing behind. Not the matter, not the particles, and not the information. It's just gone, as if it never existed. That violates quantum theory. And when two fundamental pillars of physics contradict each other, something is very, very wrong. This is the black hole information paradox. Stephen Hawking brought it into the spotlight, and for decades, no one could resolve it. If information is destroyed, quantum mechanics collapses. If information escapes, we have to rewrite what we know about space, time, and black holes. And either way, reality bends. Imagine someone throwing a book into a black hole. That book contains words, structure, meaning, quantum information. If the black hole just radiates out heat, featureless, bland, unrecognizable, then the information in that book is lost. Not just physically, but fundamentally. It no longer exists in the universe. The laws that governed it, broken. That's not just a problem for science, it's a nightmare for reality. It means the universe is not a safe archive. It forgets. It decays. It lies. Some theories try to fix this. Maybe the information is encoded in the Hawking radiation somehow. Subtle, tangled, nearly impossible to decode. Others say it clings to the event horizon, like a hologram, storing a two-dimensional shadow of a three-dimensional truth. This is the holographic principle, and it's one of the most radical ideas in modern physics, that the universe itself might be a projection, that everything we see is just a surface illusion, hiding information smeared across the edges of space. But there's another darker possibility. That information really is destroyed, that black holes do erase the script, that the universe is leaking data with every star it consumes. And if that's true, then we're living in a corrupted file, a glitchy simulation, a world where some parts of the code just vanish. And if information can disappear there, what makes you think it can't disappear here? Memories, identity, consciousness. What if they're not as durable as we think? What if the mind, like matter, can fall into an event horizon of its own? Loss, trauma, sleep, and emerge with parts missing. The black hole. Information paradox isn't just about distant stars and dead galaxies. It's about the value of memory, the security of identity, the fear that who we are can be eaten by something we can't understand. Maybe death is a kind of black hole. Maybe forgetting is too. You go in. You don't come out the same. And no one, not even you, can remember what was lost. Because somewhere, deep in the dark, the universe may already be rewriting itself. One bit of missing information at a time. You've been taught that the universe is made of particles. Tiny indivisible points, electrons, quarks, photons, zipping around, combining, repelling, obeying invisible forces. But zoom in deeper, past atoms, past protons and neutrons, past everything you think is solid. You'll find something strange, not particles, not even points, but strings, tiny, vibrating strings, one-dimensional filaments of energy, unimaginably small, dancing through space. That's the idea behind string theory. And if it's right, it's not just a theory. It's the code behind reality. It's the sheet music of existence. Every particle you've ever heard of? Just a different vibration. Electrons are strings vibrating one way. Photons, another. Gravity, also a vibration. In this view, everything, from the stars to your thoughts, is made from the same fundamental thing, string. But it's not just a new kind of matter. String theory rewrites the very fabric of physics, because these strings don't just exist in 3 dimensions, they demand more, 10, maybe 11. Hidden dimensions, curled up in ways we can't see, like extra rooms in a house we never enter. But they're there, shaping the way strings vibrate, shaping the laws of nature itself. This isn't just poetic, it's precise. String theory was born from the desperate need to unify the two great forces of physics: quantum mechanics, which governs the very small, and general relativity, which rules the very large. Alone, they work. Together, they break. Gravity refuses to fit in the quantum box. String theory might be the only theory that allows them to coexist. It naturally includes gravity as one of its vibrations. That alone makes it special, maybe even final. But there's a problem. String theory doesn't predict one universe. It predicts a multiverse, a near infinite number of possible realities, each with different physical laws, depending on how those extra dimensions are folded. That's not a flaw. That's the feature. And it means everything we know, our constants, our chemistry, our biology, might be the result of a cosmic accident. Our universe, just one song in an eternal playlist. And yet, we can't test it. Not directly. Strings are too small, the dimensions too hidden, the energy's too high. Critics say it's not science, it's philosophy wrapped in math. But if it's true, it changes everything. The building blocks of reality are not solid. They're not even static. They are rhythm, oscillation, harmony. Meaning, perhaps, isn't written in matter. It's sung in vibration. So ask yourself, what if you're not made of particles at all? What if you're a melody, one unique arrangement in an infinite orchestra? What if identity, memory, even emotion are just patterns in a deeper music? And what if death is not the end of the song, but a return to silence, waiting to be retuned? Because maybe reality isn't built. Maybe it's played. One note, one frequency, one vibrating string at a time. There are moments in science when everything breaks. Not with a bang, but with a whisper. Quiet, confusing, terrifying. The double slit experiment is one of those moments. A simple setup. A beam of particles, say, electrons, fired at a barrier with two narrow slits. Behind that, a screen that records where the particles land. Harmless, straightforward. But what happens doesn't make sense, not even to the laws of physics. When you fire electrons, one at a time, you expect them to behave like bullets, go through one slit or the other, form two clusters on the screen. But that's not what happens. They form an interference pattern, a wave pattern, as if each electron split in two, as if it went through both slits at the same time, as if it wasn't a particle at all, but a wave of possibilities interfering with itself. Reality, it seems, doesn't decide what it is until it's forced to. But then we added something, a detector, a simple device to observe which slit each electron went through. And the moment we did that, everything changed. The interference pattern vanished. The electrons stopped behaving like waves. They behaved like particles again, as if the act of watching collapsed the mystery into certainty, as if reality itself knew it was being observed and obeyed. Let that sink in. Observation didn't just reveal the state of the system, it changed it. The electron's path wasn't decided until we looked, not metaphorically, literally. Until then, it existed in a superposition, multiple states at once. Possibility, not certainty. But once we measured it, the wave function collapsed, and what was potential became fact, meaning the line between what is real and what is watched may not exist at all. This isn't just some strange quantum trick. It's a direct challenge to your understanding of reality. It suggests that the universe isn't made of solid facts, but of probabilities, smeared across time and space. waiting to be shaped by your attention. And if particles behave differently when we observe them, what about larger systems? What about thought, emotion, memory? Are they also waiting to be collapsed by perception? Some theorists say consciousness itself may be entangled with the quantum world, that your awareness may influence the fabric of reality in ways we don't yet understand, that to observe is to participate in creation, that the universe is not a machine running on autopilot, but a kind of mirror, responding, reacting, staring back. Think about that. Every time you look at something, you're not just seeing it, you're finalizing it. Your act of perception forces the world to choose. Every glance is a demand, every observation, a command. And if the universe listens, what does that make you? Maybe you're not just in the simulation. Maybe you're part of the code, a fragment of awareness that turns possibility into presence. And maybe reality, in its purest form, isn't made of matter at all, but of questions. Questions looking for answers. Waves waiting for collapse. Existence waiting to be known. And maybe that's the truth we've always feared. The universe doesn't exist without you. Imagine you're staring at a wall, solid, impenetrable, immovable. In every logical sense, you're trapped on one side. No matter how fast you run or how hard you try, that wall will stop you. That's how the classical world works. Predictable, mechanical, fair. But in the quantum world, the rules don't care about logic. In the quantum world, you might just vanish and reappear on the other side. This is quantum tunneling, a phenomenon so strange, so paradoxical, it violates everything you thought you knew about barriers, boundaries, and cause and effect. You see, in the realm of the very small, particles don't behave like tiny marbles. They act like waves of possibility, smears of existence stretched across space. And when a wave hits a barrier, something surreal happens. There's a chance, a very small chance, that part of that wave doesn't reflect. It passes through, not around, not over, through. It's not that the particle climbs over the wall. It doesn't break through it either. It just appears on the other side, like reality blinked, like the rules of space and time flickered just for a moment. And in that moment, the impossible became inevitable. This isn't some fringe theory. It's real. It's the reason nuclear fusion happens in the sun, despite the particles not having enough energy to overcome their repulsive forces. It's the principle behind quantum tunneling microscopes, semiconductors, and even the radioactive decay of atoms. Without it, life itself couldn't exist. Without it, stars wouldn't shine. But what does it mean? If particles can tunnel through barriers, they shouldn't be able to cross. What does that say about the nature of reality? Are we living in a universe governed by chance, by blind probability, where particles don't obey certainty but flirt with the forbidden? Or is something deeper happening? Something that transcends time, space, and matter? Some physicists propose that tunneling is more than just a quirk, that it points to a hidden layer of reality, a place where all possibilities coexist, and what we call impossible is just a low probability outcome. A universe not ruled by absolutes, but by waves of probability crashing against walls, and sometimes leaking through. But if particles can pass through barriers, maybe boundaries aren't what we think they are. Maybe the separation between objects, people, even minds, maybe those two are just thin walls in a quantum fog. Could our thoughts, dreams, or even identities be capable of tunneling? Not physically, but existentially. Because if matter can defy the laws of location, maybe you can defy the laws of limitation. Maybe you're already tunneling through identities, through timelines, through who you were and who you're becoming. Maybe every choice is a potential escape, every thought a probability wave, and every impossible situation just another wall waiting to be ignored by the rules of deeper reality. Because in the quantum world, the impossible doesn't stay impossible for long. It just waits for its chance to slip through. We experience reality as a three-dimensional world, a place where we walk, breathe, and feel. We see objects, touch surfaces, and watch the stars. It all seems so real, doesn't it? But what if I told you that everything around you, this world you trust with your senses, might not be as solid as you think? What if this entire universe, every atom, every planet, every galaxy, was nothing more than a projection, a hologram? The holographic principle is an idea that flips everything we know on its head. It suggests that our three-dimensional reality, the vast expanse of space and time, isn't the fundamental layer of existence. It's a shadow, a projection of something deeper and more abstract, a two-dimensional surface. Think of a hologram, flat, two-dimensional, but with depth and dimension seemingly projected from nowhere. Now imagine that this two-dimensional surface isn't some shiny plastic card, but the entire universe, all the matter, all the energy, all the information in this cosmos, encoded on a vast, distant horizon. It sounds like science fiction, but it's not. It's deeply rooted in theoretical physics and has been supported by mind-bending theories like black hole physics. The idea first emerged from the study of black holes, those cosmic enigmas where gravity is so strong that nothing, not even light, can escape. Physicists found that black holes could only store so much information. The amount of data inside a black hole seemed to be proportional to the surface area of its event horizon, not its volume. This suggested that all the information within the black hole could be encoded on its surface, rather than existing in its interior. In other words, the information in three-dimensional space might only exist as a projection of a two-dimensional surface. This is where the holographic principle came to life. If the information of the universe can be encoded in two dimensions, then our perception of three-dimensional space could just be a vast illusion. It's a clever trick, a cosmic sleight of hand, a mirage we take for reality. What we feel as depth, space, and substance is merely a projection of information laid out in a way we can't directly perceive. And it doesn't stop there. If our universe is a hologram, then where does the projection come from? Some theories suggest it might be encoded at the edges of the cosmos, on the so-called cosmic horizon. The universe, in this view, is a projection from a distant boundary we can't see or access. What we perceive as reality might be a vast, interconnected system of information, and we, our entire existence, could be the result of data being processed in an extraordinary, unseen realm. But what does this mean for us, here and now? For one, it challenges the very nature of space and time. It hints at a universe where the fundamental laws of reality, the laws of physics, might be a consequence of something even deeper. A process that's beyond our understanding, beyond our senses. If everything we know and experience is just a projection, then what is the true nature of the universe? Is there a hidden layer of existence beyond the hologram we live in? Are we merely pixels in the grand design? Is the universe, in essence, an illusion? If the holographic principle holds, we might not be confined to the limits of our physical world. The very idea that the universe is a projection implies that there is a deeper reality beneath the surface, one that we can't yet understand, one that may defy all the concepts we cling to. The idea that everything we see and feel is encoded information challenges us to reconsider the nature of our existence. What if our lives, our experiences, our very thoughts are just an elaborate projection, a story written on the surface of a cosmic sheet? What if we are nothing more than data, complex and beautiful, but ultimately a series of encoded patterns unfolding across time? The universe might not be made of the stuff we think it is. It might not even exist in the way we've always imagined. And if the holographic principle is correct, then the line between real and imagined may not be as clear-cut as we think. The very walls of reality, it seems, might be nothing more than a shimmering illusion, a projection from the edges of space, sent through the veil of perception. And as for us, perhaps we're just observers in a cosmic play, watching the holographic image of reality unfold before our eyes. The question remains, can we ever escape the projection? Or are we forever trapped inside the image? This is wave-particle duality, one of the most perplexing and paradoxical ideas in quantum mechanics. It tells us that on a microscopic level, particles like electrons and photons don't belong to a single category. They are both waves and particles. At one moment, they act like discrete little bits of matter, moving in straight lines, interacting with other particles. But in the next, they act like waves, spread out across space, capable of interference and defying our usual understanding of time and space. This duality was first uncovered by experiments like the double slit experiment. When light is passed through two slits, it creates an interference pattern, like the overlapping ripples of two stones thrown into a pond. This is a behavior of waves, not particles. But when scientists tried to observe which slit the light passed through, the interference pattern collapsed. The light seemed to behave like a particle, a discrete entity going through one slit or the other. The act of observation changed the behavior of the light. It was as if the universe itself was waiting for you to look before deciding what it would do. So, what are these particles? Are they waves, or are they particles? Or is it possible that they are both? The answer lies in the very fabric of reality itself. At the quantum level, the universe doesn't operate like the predictable world we can see and touch. Instead, it exists in a state of probability. Particles aren't in one place or another. They exist as probability waves. They are spread out across all possible locations until you measure them. Only then do they collapse into a single point, becoming a particle. But if the particle is both a wave and a particle, does that mean reality is something far more fluid than we think? Is our experience of the world just a limited projection of the deeper, hidden layers of existence? In the world of the very small, everything is uncertain, shifting between states. Perhaps the same uncertainty is built into our lives. Maybe the boundaries of our own identity, our own existence, are not as rigid as we think. Maybe we too exist in a kind of wave-particle duality. What if everything you think you know about your life, your purpose, your identity, isn't as fixed as you believe? Perhaps the world isn't as stable as it seems, but a swirling sea of possibilities, waiting for your observation to force it into a single reality. Maybe the uncertainty of quantum mechanics is mirrored in your own choices, your own thoughts. Maybe we all exist in a state of probability, a state of potentiality, where the act of observation, of deciding, is what locks us into the version of reality we live. If particles can exist as both waves and particles, then maybe our very perception of reality is an illusion. Perhaps the universe is not a solid, unchanging place. Maybe it's more like a dream, a vision of probabilities that only solidify when we choose to look, to measure, to define. Every choice you make could be shaping your reality in ways you don't even understand, just like the particle that becomes a wave, and the wave that becomes a particle. In the end, wave-particle duality isn't just a strange feature of quantum physics. It's a window into the deeper nature of reality itself. The world we see, feel, and touch might be nothing more than an illusion, a snapshot of probabilities collapsing into a single point. And perhaps, as we look closer, we'll discover that we're not just spectators of this universe. We are part of its mystery, its uncertainty, its very fabric. Imagine a storm brewing in the sky. Dark clouds swirling, lightning crackling through the air, thunder rumbling in the distance. On the surface, it seems chaotic, uncontrollable, a force of nature that defies all attempts at prediction. The winds are unpredictable. The rain falls in torrents, and everything seems to be falling apart. But beneath the chaos, something strange is happening. Something subtle, something profound. What if I told you that in this chaos, there is order? What if I told you that chaos, something we see as randomness and destruction, is actually governed by hidden rules? That beneath the surface, even the most unpredictable events are following an underlying pattern, one we don't always see, but that's always there, shaping the very fabric of our reality. This is the essence of chaos theory, the study of complex systems whose behavior is highly sensitive to initial conditions, often described as the butterfly effect. Small changes in the starting point of a system can lead to vastly different outcomes, making long-term prediction almost impossible. This doesn't mean that the system is random. Instead, it means that the system's evolution is so complex that even the smallest fluctuation can cause a cascading effect, spiraling the system into unexpected territory. In other words, chaos isn't just disorder, it's order hidden beneath complexity. Think about the famous example of a butterfly flapping its wings in one part of the world. According to chaos theory, this tiny, seemingly insignificant action could set off a chain of events that leads to a tornado halfway across the globe. The idea seems absurd, doesn't it? But it speaks to the heart of what chaos theory reveals, that the universe is intricately interconnected, and small events can have massive consequences. A single flap of the wings can alter the trajectory of a hurricane. A small decision you make today could echo throughout your life in ways you can't begin to predict. Chaos theory has its roots in the study of dynamic systems, systems that evolve over time, like the weather, the stock market, or even the human brain. These systems can behave unpredictably, but they are not truly random. They follow mathematical equations, often called nonlinear dynamics, that reveal hidden patterns beneath the chaos. It's as if the universe is a grand, complex puzzle, and while we can't always see the pieces or how they fit together, there is a deeper logic at play. Take the example of the weather. Meteorologists can predict the weather in the short term fairly accurately, but try to predict the weather months ahead, and you'll quickly realize it's nearly impossible. This is because small, seemingly insignificant factors, like a bird flapping its wings, can drastically alter the outcome. The weather is a chaotic system, and while it follows certain rules, it's highly sensitive to initial conditions, making long-term predictions futile. And yet, despite this unpredictability, there's an inherent order in the system. The patterns that emerge over time, though complex, are not random. They follow fractals, self-repeating patterns that emerge at every scale of observation. If you zoom in on a seemingly chaotic coastline, for example, you'll see that it repeats itself on smaller and smaller scales. The coastlines of the world are fractals, much like the branches of a tree or the veins in a leaf. The more you look, the more you begin to see that the chaos is simply the same pattern unfolding at different scales, at different levels of complexity. This hidden order in chaos speaks to something much deeper than mere weather patterns or stock market fluctuations. It suggests that our world, despite appearing random and uncontrollable, is full of intricate systems and patterns we can't always see. Our lives, too, may be shaped by these invisible forces. Small decisions, tiny actions, unexpected events that ripple outward in ways we may never fully understand. Chaos. Theory forces us to confront the uncomfortable truth that we are not always in control. The systems we inhabit are often unpredictable, and the consequences of our actions can be far-reaching in ways we cannot predict. But this isn't something to fear. In fact, it's the essence of the beauty and mystery of life. We are all part of this chaotic, interconnected web of existence. And in that chaos, we find the hidden order that shapes our universe. Patterns emerging from disorder, meaning arising from randomness. Perhaps, like the butterfly flapping its wings, you too have an impact that stretches far beyond what you can see. Every action you take, every choice you make, may be part of a larger pattern, a deeper order in the universe that you'll never fully grasp. And maybe that's the point, to embrace the chaos, knowing that there is something beautiful in its unpredictability, something meaningful hidden beneath the surface of disorder. We live in a universe that's far stranger than we could ever imagine. Our eyes are trained to see a world full of familiar objects, stars, planets, galaxies, and the endless stretch of space between them. We look up at the night sky, and we think we know what's out there. But there's something we can't see. Something vast, powerful, and invisible. Something that makes up most of the universe, yet it's not something we can observe directly. Dark matter and dark energy are the elusive forces that shape the cosmos, but we can't see them, touch them, or fully understand them. They remain hidden, not because they are small or fleeting, but because they are, quite literally, invisible. Dark matter accounts for roughly 27% of the universe's mass energy content, while dark energy makes up a staggering 68%. That means 95% of the universe is made up of these invisible, mysterious substances. And yet, we only truly understand the other 5%. Let's begin with dark matter. If you look at a galaxy, it seems like it's held together by the gravity of the stars, planets, and gas within it. But when scientists began measuring how galaxies spin, they noticed something strange. The stars on the outer edges of galaxies were moving faster than they should be, according to the amount of visible matter present. There wasn't enough visible matter to explain the way the galaxy was behaving. It was as if there was something else, something invisible, providing extra gravitational pull, holding everything together. This is where dark matter comes in. Though we can't see it, we know it's there because of its gravitational effects on the objects we can observe. It doesn't emit, absorb, or reflect light. which is why we call it dark. It interacts with normal matter through gravity, but it doesn't interact with electromagnetic forces in the way regular matter does. Despite its elusiveness, scientists are certain that dark matter exists because of its profound effects on galaxies, galaxy clusters, and the structure of the universe itself. Now, let's turn to dark energy, the even more mysterious of the two. In the late 1990s, astronomers made an extraordinary discovery. As they studied the expansion of the universe, they realized that the universe wasn't just expanding, it was expanding at an ever-increasing rate. This accelerated expansion couldn't be explained by the gravitational pull of matter alone. Something else was pushing the universe apart, something powerful and invisible. This force was dubbed dark energy. Dark energy is thought to be responsible for about 68% of the total energy content of the universe. Unlike dark matter, which has mass and pulls objects together with gravity, dark energy works in the opposite direction. It pushes everything apart, causing the universe to expand at an accelerating rate. But just like dark matter, we can't directly observe dark energy. We know it's there because of its impact on the expansion of the cosmos, but we don't know what it is or how it works. The truth is, we don't fully understand either dark matter or dark energy, but they are crucial to our understanding of the universe. Without dark matter, galaxies wouldn't hold together. Without dark energy, the expansion of the universe would be slowing down instead of speeding up. Both forces are integral to the cosmic dance that shapes everything we know, and everything we can't even begin to comprehend. But here's the real question. If 95% of the universe is invisible, what does that mean for us? What if our understanding of the universe is built on a foundation that we can barely see? What if the reality we experience is only a fraction of the true cosmos, and we're trapped in a bubble of perception, unable to comprehend the larger truths around us? Is it possible that our world is shaped by forces so vast, so pervasive, that we're blind to them? Dark matter and dark energy might be the most profound reminders that we don't have all the answers. Our perception of the universe is limited by our senses, our instruments, and our understanding. But we're learning. With each discovery, each breakthrough, we inch closer to unraveling the mysteries of the cosmos. And who knows what we'll find when we finally peer into the darkness. Perhaps the greatest lesson of dark matter and dark energy is that there is so much more to the universe than what we can see. The unknown forces that shape reality, forces we can't perceive with our senses, are driving the expansion of the universe, determining the fate of galaxies, and weaving the very fabric of existence. If 95% of the universe is hidden from us, what does that tell us about the limits of human knowledge? How much of reality remains invisible, waiting to be uncovered? As we delve deeper into the mysteries of dark matter and dark energy, we might just discover that the universe is far more strange, complex, and mysterious than we could ever have imagined. And maybe, just maybe, the biggest secrets lie in the things we cannot see at all. The quantum Zeno effect is one of the strangest and most fascinating phenomena in quantum mechanics. At its core, it suggests that the act of constant observation can prevent a quantum system from changing. In other words, if you measure a system frequently enough, you can freeze it in its current state. This idea is rooted in the principles of quantum superposition and measurement. In quantum systems, particles don't have definite properties until they are measured. Instead, they exist in a cloud of probabilities. When a measurement is made, the system collapses into a specific state. But if you keep measuring it rapidly, you keep collapsing the wave function back to the same state over and over again, essentially preventing it from evolving naturally. This effect was first proposed in the 1970s and seemed counterintuitive, even paradoxical. Yet, it has been experimentally verified. In controlled lab conditions, scientists have used trapped ions and unstable atoms to demonstrate that frequent measurements can indeed inhibit quantum transitions. For example, they've prevented atoms from decaying by continuously checking their state. In the absence of measurement, these atoms would naturally decay after a certain time. But under rapid observation, they remained in their excited state far longer than expected. The implications of the quantum Zeno effect are profound. It challenges our classical intuitions about time, motion, and observation. It also raises philosophical questions about the role of consciousness and measurement in shaping reality. Some interpretations suggest that the very act of observing not only influences, but determines what exists. While not directly tied to consciousness, this idea often intersects with debates in quantum foundations about the observer's role. Practically, the effect also has relevance in quantum computing and quantum control. By understanding how to manipulate and stabilize quantum states through observation, researchers can work toward maintaining coherence in quantum systems, which is essential for building reliable quantum technologies. The quantum Zeno effect is a vivid reminder that in the quantum world, the simple act of looking can change everything. Time crystals are a newly discovered and incredibly strange phase of matter that break one of the most fundamental assumptions in physics, that the ground state of a system must be time invariant. In normal crystals, atoms are arranged in repeating patterns across space. In time crystals, this pattern repeats not in space, but in time. The atoms oscillate between configurations in a regular, predictable rhythm, without any input of energy. This means the system moves perpetually, even in its lowest energy state, defying the traditional rules of thermodynamics. The concept was first proposed by Nobel laureate Frank Wilczek in 2012. Initially, it seemed like a purely theoretical idea, bordering on impossible. But in 2016 and 2017, experimental breakthroughs showed that time crystals could be created in lab settings, using systems like trapped ions and superconducting qubits. These time crystals don't violate energy conservation laws because their motion is not the same as perpetual motion machines in classical physics. They don't output work. Instead, they display motion in a system that should be static, governed by interactions and quantum coherence. One of the key features of time crystals is that they spontaneously break time translation symmetry, meaning they naturally settle into a rhythm that's different from the periodic driving force applied to them. This kind of symmetry breaking is unprecedented. It's like pushing a swing every 2 seconds and watching it swing back and forth every 4 seconds instead, completely on its own rhythm. Time crystals could have significant implications for quantum computing. Because they operate in a kind of protected, repeating state, they may help develop systems that are more resistant to decoherence. One of the main challenges in maintaining stable quantum bits over time. In this way, time crystals are not just theoretical curiosities, but may point toward practical technologies. The discovery of time crystals expands our understanding of what phases of matter are possible. It also challenges long-held beliefs about stability, motion, and energy. In a universe governed by entropy and decay, time crystals seem to whisper of a hidden order, an exception to the rule that even time must eventually come to rest. Closed time-like curves are solutions to the equations of general relativity that suggest time travel to the past could be theoretically possible. In essence, a closed time-like curve, or CTC, is a path through the fabric of space-time that loops back on itself, If an object were to follow this path, it could return to the exact point in spacetime from which it started, effectively creating a closed loop in time. These curves arise in highly curved spacetimes, such as those near massive rotating bodies, or in theoretical constructs like wormholes or cosmic strings. One of the earliest models proposing CTCs was Kurt Gödel's rotating universe solution in 1949, where he showed that general relativity allowed for a universe filled with rotating matter that would permit time travel. Later, other theorists expanded on this with ideas like the Tipler cylinder, a rotating, infinitely long cylinder, and traversable wormholes stabilized by exotic matter, which could also create conditions for CTCs. However, all these solutions either require unrealistic physical conditions, such as negative energy or infinite structures, or lead to paradoxes that challenge our understanding of causality. The most famous paradox associated with closed time-like curves is the grandfather paradox. If you traveled back in time and prevented your grandfather from meeting your grandmother, you would never have been born, meaning you couldn't have gone back in time in the first place. This kind of logical contradiction highlights the potential instability of any physical system that allows time loops. Some physicists have attempted to resolve these issues with concepts like the Novikov self-consistency principle, which suggests that events along a closed time-like curve are constrained to be self-consistent, meaning paradoxes can't occur because the timeline always resolves in a logically coherent way. Despite the theoretical groundwork, there is no experimental evidence that CTCs exist in our universe. Moreover, many physicists believe that a full theory of quantum gravity might ultimately forbid such structures, preserving the arrow of time and causality. Still, closed time-like curves remain a fascinating possibility within Einstein's theory. A thought experiment that forces us to confront the limits of physics, logic, and perhaps even free will. Observer-dependent reality in relativity refers to one of the most profound and unsettling implications of Einstein's theory. The idea that reality itself is not absolute, but depends on the observer's frame of reference. In both special and general relativity, quantities like time, distance, simultaneity, and even the order of events can change depending on how fast someone is moving or how close they are to a massive object. What one observer sees as two events happening at the same time, another observer might see as occurring at different times. Both perspectives are equally valid within their own frames. This isn't just a theoretical oddity. It's been confirmed by experiments involving atomic clocks flown around the Earth and particles moving at near light speed. Time dilation, for instance, shows that a moving observer experiences time more slowly relative to someone at rest. This means that two people moving at different speeds or in different gravitational fields will age at different rates. The famous twin paradox is a direct result of this principle. One twin travels through space and returns younger than the twin who stayed on Earth. Perhaps the most mind-bending aspect is the relativity of simultaneity. In classical physics, time is the same for everyone, an absolute backdrop to all events. But in Einstein's framework, simultaneity is not universal. If two lightning bolts strike at the same time, according to someone standing still on a train platform, a person on a fast-moving train might see one bolt strike before the other. There is no single, objective answer to which event happened first. Only frame-dependent truths. This challenges the notion of a single, shared reality. Instead, reality splinters into a web of observer-specific versions, all equally true within their context. It undermines the classical idea of a fixed universe, unfolding identically for all observers. While relativity doesn't deny the existence of an external reality, it shows that our perception of it is fundamentally shaped by our position, motion, and perspective. In this way, observer-dependent reality isn't just a feature of relativity, it's a deep philosophical shift in how we understand the universe itself. Quantum eraser experiments reveal one of the most bizarre and counterintuitive aspects of quantum mechanics, that the act of gaining or erasing information can alter the past behavior of a quantum particle. These experiments build on the famous double slit experiment, where particles like photons or electrons create an interference pattern when not observed, suggesting they behave like waves. But when observed to determine which slit they pass through, the interference pattern disappears, and the particles behave like classical particles instead. The quantum eraser takes this a step further. In these experiments, which path information is recorded and then either preserved or erased after the particle has gone through the slits. What's remarkable is that when the which path information is erased, even after the detection, the interference pattern returns. It's as if the particle retroactively decides whether it acted like a wave or a particle, based on whether the observer can know its path. The delayed choice quantum eraser, a specific version of the experiment, shows that choices made in the present can influence outcomes in the past, at least statistically. These results don't allow for communication back in time or violations of causality, but they do challenge our classical understanding of time and reality. The fact that measurement and knowledge, or the potential for knowledge, can shape the physical outcome of an experiment implies that reality at the quantum level is not fixed until it's observed, and even the potential to observe has profound consequences. Quantum eraser experiments are not just theoretical curiosities. They have practical implications for quantum information science, especially in understanding the nature of entanglement and decoherence. But on a deeper level, they highlight one of the core mysteries of quantum mechanics: the role of the observer and the apparent dependency of the physical world on whether or not information exists about it. In these experiments, the universe seems to ask, not what happened, but what could be known, a question that continues to blur the line between physics and philosophy. Renormalization in quantum field theory might sound like one of those intimidating physics buzzwords, but it's actually one of the most clever and weirdly necessary tricks in the modern physicist's toolkit. Imagine trying to calculate how particles like electrons interact, and suddenly your math spits out infinity. Not once, but every time. You're not doing anything wrong. It's just that, in the quantum world, things get messy when you try to deal with all the virtual particles, vacuum fluctuations, and high-energy possibilities involved in even the simplest interactions. Here's where renormalization steps in. Instead of panicking over those infinities, physicists realized, hey, maybe those bare values, like the raw charge or mass of a particle, aren't what we actually observe. What we do measure is a version of those values, dressed up by quantum fuzziness. So, we redefine things. We subtract the infinities, adjust the parameters, and reframe the problem so the final answers are finite, measurable, and, surprisingly, super accurate. Take quantum electrodynamics, QED, for example. Renormalization is the reason it can make predictions that match experiments to more than 10 decimal places. It's precision physics at its finest, and it earned people like Feynman, Schwinger, and Tominaga the Nobel Prize. Without renormalization, QED, and by extension, the entire standard model, would collapse under the weight of its own infinities. But here's the trippy part. Renormalization tells us that some parts of our equations aren't really real. They're placeholders, scaffolding we build to support calculations that ultimately make sense in the world we observe. At very high energies, our theories might just fall apart. It's like using a map that only works within a certain city, great for local travel, but useless once you hit the edge. So renormalization is both brilliant and unsettling. It works so well it's hard to argue with, yet it constantly whispers that our theories might be patchwork, provisional models that make sense now, but are incomplete. It's one of those rare tools in science that simultaneously solves the problem and points to deeper ones lurking beneath. The Einstein-Rosen bridge, better known today as a wormhole, is one of the most fascinating and mind-bending predictions to emerge from general relativity. Originally proposed in 1935 by Albert Einstein and Nathan Rosen, this theoretical structure is a tunnel-like shortcut through space-time, connecting two distant points in the universe. If such a bridge could exist and be traversable, it would allow for instantaneous travel across vast cosmic distances, or perhaps even between different universes. In Einstein and Rosen's original formulation, the wormhole appeared as a mathematical extension of the Schwarzschild solution, which describes black holes. The idea was that every black hole might be connected to a white hole in another region of space-time, a mirror image that expels matter instead of pulling it in. The geometry formed between the two was a bridge-like structure, but there was a catch. Their solution described a wormhole that would collapse too quickly for anything, even light, to pass through. In other words, it existed mathematically, but not practically. Decades later, the concept was revitalized by physicists like Kip Thorne and Michael Morris, who explored the possibility of traversable wormholes, structures that could potentially allow matter and information to pass through. But to do this, you'd need exotic matter with negative energy density to hold the wormhole open. This kind of matter isn't something we encounter in everyday physics, and its existence is speculative at best. Though quantum effects like the Casimir Effect hint that negative energy is not entirely impossible. Wormholes open up tantalizing possibilities. Faster than light travel, shortcuts across galaxies, even time travel under specific conditions. But with these possibilities come paradoxes. A traversable wormhole could allow someone to travel back in time and alter events, violating causality and creating the infamous grandfather paradox. Some physicists argue that quantum effects, or as yet unknown laws of gravity, might prevent these contradictions, effectively protecting the timeline. So far, no evidence has been found that wormholes exist in nature, but the mathematics is sound, and the idea continues to inspire both scientific inquiry and science fiction. Whether they're real or not, Einstein-Rosen bridges challenge our understanding of space, time, and the ultimate structure of reality. And they remind us that even in the cold equations of general relativity, there's still room for cosmic wonder. Reversible and irreversible processes are two fundamental concepts in thermodynamics, and they define how energy moves and transforms in systems, affecting everything from heat engines to the fundamental nature of time itself. A reversible process is a theoretical concept in which a system undergoes a change, so that, if the process is reversed, the system can return to its original state, with no loss of energy and no increase in disorder. In a reversible process, everything happens slowly and in equilibrium, allowing the system to adjust at every moment without creating any gradients, no differences in temperature, pressure, or other properties. A common example is the expansion or compression of an ideal gas in a frictionless piston at an infinitesimally slow rate. In such a case, the system can be reversed at any point, and the work done by the gas can be completely recovered. However, it's important to note that a perfectly reversible process is an idealization. In reality, such processes don't exist because of factors like friction, heat loss, and other dissipative effects. On the other hand, irreversible processes are much more common in nature and represent changes in a system where energy or matter is dispersed in a way that cannot be fully reversed. These processes generate entropy, which is the measure of disorder or randomness in a system. In an irreversible process, energy is dissipated as heat, and the system becomes more disordered, often moving toward equilibrium. A typical example of an irreversible process is the spontaneous mixing of two different gases, or the expansion of a gas into a vacuum. In both cases, the process cannot be easily reversed without additional work or energy input. The key difference between the two types of processes is entropy. In a reversible process, entropy remains constant, while in an irreversible process, entropy increases. This is a direct consequence of the second law of thermodynamics, which states that the total entropy of an isolated system can never decrease, and it usually increases over time as energy becomes more spread out and less usable. Irreversible processes have profound implications for the world we experience. They introduce the concept of the arrow of time, suggesting that time itself flows in one direction, toward greater entropy and disorder. While a reversible process might theoretically happen both ways, an irreversible one marks a distinct transition from order to disorder that can't be undone. This irreversibility is not just a thermodynamic idea, but a fundamental feature of our universe, dictating the direction of many natural processes, from the cooling of hot objects to the burning of fuel, and even the evolution of the cosmos itself. In short, while reversible processes are theoretical ideals that allow us to understand the limits of efficiency, irreversible processes define the real world of energy dissipation, entropy generation, and the inevitable march toward equilibrium. Mach's principle is a concept in theoretical physics and cosmology that suggests the inertia of an object, the resistance it experiences when trying to accelerate, is not intrinsic to the object itself, but is instead influenced by the gravitational interaction with the entire universe. In other words, the mass and motion of distant objects and the distribution of matter in the universe affect the inertia of an object within a local system. This idea was first proposed by the 19th century philosopher and physicist Ernst Mach, and it challenges the classical Newtonian view of inertia. In Newton's laws, inertia is an inherent property of matter. Objects resist changes in motion, regardless of their position in the universe. However, Mach argued that the inertia of a body must be determined by its interaction with the rest of the universe. In his view, if the universe were empty, an object would not experience any resistance to motion, because there would be no other masses to interact with. Mach's principle inspired Albert Einstein, particularly during the development of his theory of general relativity. While Einstein did not adopt Mach's principle in its entirety, it helped him think about how the geometry of space-time and the distribution of mass and energy could influence the motion of objects. In general relativity, inertia is influenced by the curvature of space-time, which is shaped by the presence of mass and energy. Mach's idea that inertia is related to the distant matter in the universe provided some inspiration for how Einstein formulated the interaction between mass and space-time geometry. Despite its inspiration for general relativity, Mach's principle remains somewhat controversial, and is not a fully realized part of modern physics. In particular, while the theory of general relativity describes how mass curves space-time, it does not explicitly support the idea that an object's inertia is directly influenced by distant stars or galaxies. Some physicists even argue that the idea is not empirically testable and may not have any direct physical meaning. Nevertheless, Mach's principle continues to provoke deep philosophical and theoretical questions about the nature of motion, inertia, and the interconnectedness of the universe. It challenges the idea that the laws of physics are fixed in a local frame of reference, suggesting instead that the universe as a whole could be interconnected in ways that we don't yet fully understand. Although Mach's principle isn't universally accepted, it remains a significant and intriguing concept in the quest to understand the fundamental workings of the universe. The concept of the quantum vacuum as a physical medium is one of the most mind-boggling ideas in modern physics. Traditionally, a vacuum was thought to be simply empty space, nothing more than a void, devoid of matter and energy. However, quantum mechanics introduces a radically different view. Even empty space is teeming with activity. The quantum vacuum is far from empty. It is a dynamic, fluctuating field that plays a crucial role in the laws of physics. At its core, the quantum vacuum is the lowest possible energy state of a quantum field. This state may appear to be devoid of particles, but it's actually full of quantum fluctuations, random, temporary changes in the amount of energy present at a point in space. These fluctuations give rise to the creation and annihilation of particle-antiparticle pairs that pop in and out of existence in a process governed by the Heisenberg uncertainty principle. According to this principle, there is a limit to how precisely we can know certain pairs of properties, such as energy and time. This uncertainty allows for the temporary creation of energy that can manifest as virtual particles. These virtual particles are not directly observable because they exist for such brief periods of time, but their effects can be detected. One example is the Casimir Effect, where two uncharged conducting plates placed in a vacuum will experience an attractive force due to the quantum vacuum fluctuations between them. This is direct evidence that the vacuum is not empty, but filled with fluctuating energy. The quantum vacuum also plays a fundamental role in the behavior of field particles. For instance, in quantum electrodynamics, QED, the interaction between charged particles, like electrons, is mediated by virtual photons, which are excitations of the electromagnetic field. Even in a vacuum, the electromagnetic field is not truly at rest. It is constantly fluctuating. These fluctuations affect the properties of particles and fields, creating subtle forces and altering the behavior of matter in ways that would be impossible in a classical vacuum. In the realm of quantum field theory, the vacuum is considered to be the backdrop against which all particle interactions occur. It's not just a passive void, but a dynamic and active medium that has significant effects on particle physics. The idea that the vacuum itself has energy, often called zero-point energy, means that space is never truly empty. This has profound implications for everything from the stability of atomic systems to the potential for future technologies like vacuum energy extraction. The idea of harnessing the energy that exists even in empty space. Additionally, the quantum vacuum is thought to be responsible for some of the most puzzling and profound phenomena in the universe, such as dark energy, the mysterious force driving the accelerated expansion of the universe. Some theories suggest that this vacuum energy is a form of dark energy, which could account for the observed cosmic acceleration. If true, This would imply that the quantum vacuum is not just an abstract concept, but a key player in the large-scale structure and evolution of the universe. In short, the quantum vacuum is anything but empty. It is a complex energetic medium that is integral to the functioning of quantum fields and the universe at large. Its fluctuations give rise to the very particles and forces we observe, and it could even be the source of some of the most enigmatic phenomena in modern cosmology. Quantum chromodynamics, QCD, is the theory that describes the strong force, one of the four fundamental forces in nature. It governs the interactions between quarks and gluons, the fundamental particles that make up protons, neutrons, and other hadrons. The strong force is responsible for holding quarks together within these particles and binding atomic nuclei. In QCD, quarks come in 6 types, flavors: up, down, strange, charm, bottom, and top. And each quark carries a type of color charge: red, green, or blue. The force between quarks is mediated by gluons, which are massless particles that also carry color charge, enabling them to interact with one another. This self-interaction between gluons is a distinctive feature of QCD, making the theory more complex than quantum electrodynamics, QED. The key principles of QCD are confinement and asymptotic freedom. Confinement means quarks are never found alone in nature. They are always confined within larger particles, like protons and neutrons. The force between quarks becomes stronger as they try to move apart, preventing them from being isolated. Asymptotic freedom refers to the phenomenon where quarks and gluons interact more weakly at extremely short distances or high energies, a unique feature of the strong force. QCD also predicts the formation of quark-gluon plasma, a state of matter where quarks and gluons exist independently, like in the early universe right after the Big Bang. Studying this plasma can provide insights into the early conditions of the cosmos. QCD's implications go beyond theoretical physics. It plays a crucial role in high-energy particle collisions, such as those at the Large Hadron Collider, LHC, where quarks and gluons are indirectly observed. The discovery of particles like the Higgs boson has also provided new insights into the behavior of quarks and gluons. In summary, quantum chromodynamics is a key part of the standard model of particle physics, explaining how quarks and gluons interact through the strong force. While complex, its principles of confinement and asymptotic freedom are essential to understanding the structure of matter and the universe at the most fundamental level. Gravitational lensing is a phenomenon predicted by Einstein's theory of general relativity, where the gravitational field of a massive object, like a galaxy or black hole, distorts the path of light passing near it. This bending of light works much like a lens, magnifying and sometimes creating multiple images of distant objects, such as stars or galaxies, that are located behind the massive object. In essence, the gravitational field of a massive object curves space-time itself, causing light traveling through that region to follow a bent trajectory. The result is that the light from a distant object appears distorted, magnified, or even split into multiple images. There are 3 primary types of gravitational lensing: strong lensing, weak lensing, and microlensing. Strong lensing occurs when the light is bent significantly, often creating multiple distinct images of the same object. In extreme cases, this can result in phenomena like Einstein rings, where the background object appears as a ring around the lensing object. Weak lensing refers to more subtle distortions, where the background object's shape is slightly stretched or elongated due to the gravitational influence of an intervening mass. This type of lensing is often used in large-scale surveys to map the distribution of dark matter, as it provides indirect evidence of matter that cannot be seen directly. Microlensing happens when a relatively small object, like a star or planet, passes in front of a more distant object. The gravity of the intervening object acts like a magnifying glass, causing a temporary increase in brightness. Microlensing is used in the search for exoplanets and dark matter. Gravitational lensing has become an important tool in modern astronomy. By studying the distortions in light caused by lensing, astronomers can learn about the mass, composition, and structure of the lensing object, even if it's not directly observable. It also provides a way to probe distant objects that would otherwise be too faint or far away to study. Additionally, gravitational lensing offers insight into the nature of dark matter. Since lensing can occur without the presence of visible matter, the distortions can be used to detect and map dark matter, which doesn't emit light but exerts gravitational effects. This makes gravitational lensing one of the key observational methods for exploring the universe's unseen components. In summary, gravitational lensing is a powerful consequence of general relativity, where massive objects bend light in ways that reveal hidden details about the universe. By observing and analyzing these distortions, astronomers gain invaluable information about both visible and dark matter, as well as the structure of the cosmos itself. Electroweak theory is a fundamental component of the standard model of particle physics that unifies two of the four fundamental forces, the electromagnetic force and the weak nuclear force. Developed in the 1970s by Sheldon Glashow, Abdus Salam, and Steven Weinberg, the theory shows that at extremely high energies, these two forces merge into one, behaving as a single force. The photon mediates the electromagnetic force, while the W and Z bosons mediate the weak force, responsible for phenomena like radioactive decay. The theory also introduces spontaneous symmetry breaking, where, at lower energies, the forces appear distinct. This symmetry breaking was confirmed by the discovery of the Higgs boson in 2012, which explains how particles acquire mass. The Higgs boson interacts with particles through the Higgs field, giving them mass, while the electromagnetic force remains massless. Electroweak theory has been a crucial achievement in physics, though it doesn't include gravity. It remains a significant step toward understanding the fundamental forces and inspires the search for a grand unified theory that could merge all the forces. The Casimir Effect is a physical phenomenon that arises from the quantum vacuum fluctuations of space. It was first predicted in 1948 by the Dutch physicist Hendrik Casimir, and it demonstrates how empty space is not truly empty. Instead, even in a vacuum, there are fluctuating quantum fields that give rise to short-lived particle-antiparticle pairs. The Casimir effect occurs when two closely spaced, uncharged conducting plates are placed in a vacuum. Due to quantum fluctuations, virtual particles constantly appear and disappear in the space between the plates. These fluctuations create a pressure that pushes the plates toward each other. This force is extremely small but measurable, and it becomes stronger as the plates are brought closer together. The key insight behind the Casimir effect is that the vacuum is not a true empty void, but a seething field of fluctuating energies. Between the plates, the range of virtual particles is limited, creating fewer possible states than outside the plates. This imbalance results in an attractive force between the plates, which is the Casimir force. The Casimir effect has important implications for both theoretical physics and practical applications. For example, it is considered when designing nanoscale devices, as at such small scales, the Casimir force becomes significant enough to affect the operation of machinery or electronics. It also has connections to the study of quantum field theory, vacuum energy, and even the nature of space itself. In summary, the Casimir Effect highlights the strange and counterintuitive nature of quantum physics, showing that even the vacuum of space is far from empty. It's a small but measurable force that arises from the quantum fluctuations of the vacuum, and it has practical applications in nanotechnology and theoretical implications for our understanding of the universe. The CFT correspondence, also known as the anti-de Sitter conformal field theory correspondence, is a theoretical concept in string theory that proposes a relationship between two very different kinds of physical theories, one describing gravity in a curved space, ADS, and the other describing a quantum field theory, CFT, without gravity. The idea was first conjectured in 1997 by Juan Maldacena, and it has become a cornerstone of modern theoretical physics. The correspondence suggests that a theory of gravity in a space with negative curvature, such as anti-de Sitter, ADS space, can be equivalent to a non-gravitational quantum field theory that lives on the boundary of that space, a theory known as conformal field theory, CFT. In simple terms, it implies that the complex interactions between particles and fields in a quantum theory in the ADS space can be fully described by a CFT that exists on the boundary of that space, without gravity. This duality allows physicists to study problems in quantum field theory using the tools of general relativity and vice versa, which has opened up new avenues for understanding phenomena like black holes and quantum gravity. One of the most notable implications of the CFT correspondence is that it offers a way to study quantum gravity, which has traditionally been extremely difficult to reconcile with quantum mechanics. By relating a gravitational theory to a non-gravitational quantum theory, it provides insights into how gravity might work at the quantum level. The CFT correspondence also plays a significant role in understanding holography in physics, where the information about a higher dimensional space can be encoded on its boundary, akin to how a hologram encodes three-dimensional information on a two-dimensional surface. This idea has led to new insights into the nature of black holes, particularly in the context of the holographic principle, which suggests that the universe's description could be fundamentally lower dimensional than we think. In conclusion, the CFT correspondence is a groundbreaking concept in theoretical physics that connects gravitational theories in curved spaces with quantum field theories in flat spaces, providing profound insights into the nature of quantum gravity, black holes, and the structure of space-time itself. Landau's Fermi liquid theory is a cornerstone of condensed matter physics, developed by the Soviet physicist Lev Landau in 1956. The theory describes the behavior of interacting electrons in a metal or a degenerate Fermi gas at low temperatures. It revolutionized the understanding of how many-body quantum systems, such as electrons in metals, behave in the presence of interactions. At the heart of Fermi liquid theory is the concept that despite the complex interactions between particles, the collective behavior of these particles can be described in a simplified way by treating them as quasi-particles. These quasi-particles are not the original electrons, but behave similarly to free electrons, except with renormalized properties, like mass and charge. Landau's key insight was that the interactions between electrons in a metal do not fundamentally alter the nature of the Fermi surface, the boundary and momentum space that separates filled and unfilled electron states at zero temperature. Instead, the system can be described as a collection of quasi-particles that move independently, with the interactions between them modifying their behavior in a predictable way. Fermi liquid theory helps explain many properties of metals, such as specific heat, electrical conductivity, and thermal conductivity, all of which are governed by the behavior of electrons at the Fermi level. The theory also explains why most metals are good conductors, as the interactions between quasi-particles are relatively weak, allowing them to move through the material without significant scattering. One of the significant successes of Landau's Fermi liquid theory is its ability to explain the temperature dependence of the specific heat of metals, a phenomenon that had been difficult to understand. According to the theory, the specific heat at low temperatures behaves linearly with temperature, which matched experimental observations in many metals. However, the theory does have its limitations. It is not applicable to systems where the interactions between particles are too strong, or when the system is not in the liquid phase. For instance, it does not explain phenomena like high-temperature superconductivity, or the behavior of systems far from equilibrium. Despite these limitations, Landau's Fermi liquid theory remains essential for understanding the collective behavior of electrons in metals and other condensed matter systems. It provides a framework for studying the behavior of quantum systems at low temperatures, and continues to be a vital tool for theorists and experimentalists alike. The standard model of particle physics is the current, most comprehensive theory describing the fundamental particles and forces that make up the universe, excluding gravity. It explains 3 of the 4 fundamental forces: electromagnetism, the weak nuclear force, and the strong nuclear force, and defines the elementary particles such as quarks, leptons, and the force carriers like photons, W and Z bosons, and gluons. The Higgs boson, discovered in 2012, is also part of the standard model, and it plays a key role in giving particles mass through the Higgs field. While the standard model has been extraordinarily successful, explaining a wide range of phenomena and passing rigorous experimental tests with remarkable precision, it is not without its limitations. One of the major shortcomings is its inability to incorporate gravity. Gravity, described by general relativity, does not fit into the quantum framework of the standard model. This exclusion means that gravity cannot be accounted for within the model, leaving out one of the 4 fundamental forces that govern the universe. Another major limitation is the absence of explanations for dark matter and dark energy, which together account for approximately 95% of the universe's mass and energy. While dark matter interacts gravitationally, it does not interact with electromagnetic, strong, or weak forces, making it invisible to detection using the tools of the standard model. Similarly, dark energy, responsible for the accelerating expansion of the universe, has yet to be explained by the theory, and its nature remains a profound mystery. The standard model also initially predicted that neutrinos, subatomic particles that are extremely light and interact weakly with other matter, should be massless. However, experiments have shown that neutrinos do indeed possess a small but measurable mass, necessitating modifications to the standard model to accommodate this finding. Additionally, the standard model cannot fully explain the matter-antimatter asymmetry observed in the universe. According to the theory, the Big Bang should have created equal amounts of matter and antimatter, yet the observable universe is overwhelmingly composed of matter. This imbalance remains unexplained and is one of the unsolved puzzles in physics. The fine-tuning problem is another issue that arises within the standard model. Several fundamental parameters, such as the mass of the Higgs boson, must be precisely adjusted for the theory to match observational reality. This fine-tuning suggests that the standard model may be incomplete, and that there could be underlying principles or physics yet to be discovered. Finally, the hierarchy problem refers to the puzzling discrepancy between the mass of the Higgs boson and what would be expected from quantum corrections. This vast difference remains a mystery, suggesting that there might be new physics beyond the standard model that can explain these issues. While the standard model remains an incredibly successful theory, its inability to explain key aspects of the universe, such as gravity, dark matter, and the nature of neutrinos, points to the need for new theories and frameworks in the search for a more unified description of the fundamental forces of nature. The pursuit of this deeper understanding is at the heart of modern theoretical physics. The Unruh Effect is a theoretical prediction in quantum field theory that describes how an accelerating observer experiences what seems to be a warm, thermal bath of particles, even in a vacuum. This phenomenon is named after physicist William Unruh, who first proposed it in 1976. According to the Unruh Effect, while an observer at rest would perceive empty space as a vacuum, an observer undergoing acceleration would detect a field of particles at a certain temperature. This temperature is proportional to the observer's acceleration. To understand the Unruh Effect, it's important to consider the concept of vacuum fluctuations in quantum field theory. In the vacuum state, the quantum fields are never truly at rest, but fluctuate constantly, producing fleeting particle-antiparticle pairs that momentarily come into existence and then annihilate each other. These fluctuations are usually undetectable to an observer who is at rest. However, an accelerating observer perceives these fluctuations differently. Due to the acceleration, the observer is effectively moving through the quantum field, interacting with it in such a way that the fleeting particle pairs appear as real particles, creating the illusion of a warm, thermal background. The temperature of this thermal bath is given by the Unruh temperature formula, which is proportional to the acceleration of the observer and inversely proportional to the speed of light. For an observer accelerating at 1 g, the acceleration due to Earth's gravity, the temperature would be minuscule, on the order of a billionth of a Kelvin. However, in extreme cases of high acceleration, the Unruh temperature could become significant, potentially observable in particle physics experiments or near extremely high energy events in space. The Unruh Effect has profound implications for our understanding of quantum mechanics, relativity, and the nature of the vacuum. It suggests that there is no absolute state of rest or motion in the universe. What one observer perceives as empty space might be a bustling environment of quantum fluctuations to another observer in a different state of motion. It also connects the fields of general relativity and quantum field theory, highlighting how acceleration and gravitational effects might influence the behavior of quantum fields. However, despite its intriguing implications, the Unruh Effect has not yet been directly observed, partly because the accelerations required to detect a measurable temperature are enormous and practically unachievable with current technology. Still, the Unruh Effect continues to be a topic of theoretical research, as it offers deep insights into the relationship between quantum fields and the geometry of space-time, potentially influencing future studies of quantum gravity and black holes. The Heisenberg uncertainty principle is a fundamental concept in quantum mechanics that asserts it is impossible to precisely measure both the position and momentum of a particle simultaneously. The more accurately one of these properties is measured, the less precisely the other can be known. This is not due to limitations in technology, but rather an inherent feature of quantum systems. While this principle has been established in quantum mechanics for some time, its application in the context of relativity, specifically special relativity and general relativity, adds complexity to how we understand the nature of uncertainty in the universe. In special relativity, one of the key insights is that space and time are not separate entities, but instead are linked in the four-dimensional fabric of space-time. Observers moving at different speeds relative to each other will experience time and space differently. In this framework, the time-energy uncertainty relation is an important extension of the Heisenberg principle, asserting that there is a limit to how precisely energy and time can be measured simultaneously. This relationship suggests that the shorter the duration of an event, the greater the uncertainty in the energy associated with it. And conversely, the longer the event lasts, the less uncertainty there is in energy. When we consider relativistic speeds, these time dilation effects, which stretch time for observers moving at high velocities, can complicate the application of the uncertainty principle, because the measurement of time and energy becomes relative to the observer's motion. When examining relativistic particles, those that are moving at speeds close to the speed of light, the relationship between momentum and energy becomes particularly important. In relativistic physics, the total energy of a particle is linked to its momentum and mass through a well-known equation. The uncertainty principle, therefore, not only applies to position and momentum, but also to energy and time, with the uncertainties in these quantities becoming intertwined as the particle's speed approaches relativistic limits. This interconnectedness means that uncertainty in one property, like momentum, affects the uncertainty in the particle's energy as well. Another challenge arises when we consider quantum field theory in curved spacetime, which combines quantum mechanics and general relativity. In regions where spacetime is highly curved, such as near black holes or in the early universe, the usual concepts of position and momentum become less well defined. The quantum fluctuations of spacetime itself create a situation where even the fabric of space and time is subject to uncertainty. These quantum fluctuations can blur the lines between particles and fields, complicating the direct application of the Heisenberg principle in relativistic contexts. In these extreme conditions, the standard definitions of position and momentum lose their usual meanings, and a new approach is needed to understand how quantum mechanics operates in such environments. Finally, at the Planck scale, the intersection of quantum mechanics and general relativity becomes especially significant. This scale represents the point at which the effects of quantum gravity are expected to become important. Here, the Heisenberg uncertainty principle could play a crucial role in determining the structure of spacetime itself. The uncertainties in position and momentum could become so large that the very nature of space and time might become fuzzy. In such a regime, space might no longer be continuous, and the classical concepts of position and momentum could break down entirely. This suggests that to fully understand the relationship between quantum mechanics and relativity, a theory of quantum gravity is necessary to reconcile the uncertainty principle with the fabric of spacetime. In conclusion, while the Heisenberg uncertainty principle is a cornerstone of quantum mechanics, its application in relativistic contexts adds significant complexity. The interplay between the principles of relativity and the uncertainties inherent in quantum systems reveals that our traditional understanding of space, time, position, and momentum must be re-evaluated when considered under the extreme conditions of high velocity or strong gravitational fields. These challenges point toward the need for a unified theory of quantum gravity to fully understand how the uncertainty principle functions in the context of the universe's most extreme phenomena.